And then today we will enter the fourth meeting, the membrane bioreactor or MBR, where we will learn about the main membrane separation process used in MBR and membrane configuration, general MBR concept and terminology, current membrane bioreactor companies and worldwide development, and the application and challenges. Before we proceed with the main session, I would like to offer a closer introduction to our speaker by sharing their resume. Mr. Dr. Alnour Bokhary. And Dr. Alnour Bokhary is a distinguished researcher and educator in renewable energy and environmental engineering. Currently a postdoctoral fellow at Washington State University, Bioproduct Science and Engineering Laboratory. They focus on advanced biomass utilization for energy production. Dr. Bokhary holds a PhD in forest science with a specialization in renewable energy and has extensive expertise in membrane bioreactor technology, anaerobic digestion, and biomass pretreatment. With a prolific record of published research and contribution to prestigious journals, they bring profound insight into sustainable bioenergy and environmental bioprocessing solutions. And then we thrilled to welcome Dr. Alnour Bokhary to our lecture series today. Please join me in welcoming Dr. Alnour Bokhary as the present in the lecture of membrane bioreactor.
Hello, Budi.
Yes, yes.
I guess I need to share the slides first, and then I'll start the
Okay.
session.
I think you shared like the overall it's not the slides. I think you probably can share just specifics, just
Yeah,
presenting
just when I'm
here.
checking, I
Yeah, I
need to
think
see.
okay. I think you can stop sharing and then change it to just for the presentation.
Stop sharing. Okay.
Yeah. Okay. So that's good. So
Share. Actually, I need to go directly to my screen.
mhm. So can you do it, Elder?
Yes, yes, I'm
Okay.
ready, Budi.
Yeah. Yes, yes. Yeah.
Because
I
I
can
have,
see the
sorry,
desktop. So.
different files with different names.
Oh, okay. It looks good.
Okay.
Okay. Thank you. Thank you.
Yes, that's great.
Okay, go ahead.
Okay, guys, actually, it is 5 p.m. here in Washington State at the Tri-Cities, and I know it is early morning around 8 a.m., and it's hard for everyone to join. Actually, I appreciate you for signing for this presentation and attending the session. And actually, thank you, Aisha, for the nice introduction. My name is Alnour Bokhary. As you said, postdoctoral research associate at Washington State University. Actually, throughout my master's degree and PhD degree in Canada, I work with membrane technology, whether like direct filtration using ultrafiltration membrane, for hemicellulose recovery and lignin separation. And also later I used membrane bioreactor to treatment different biomass material and substrates. Currently, actually, I'm working on different pre-treatment technology to valorize lignocellulosic biomass, and also working on anaerobic digestion to improve the methane production from the several biomass types. Our topic today, as introduced, will be about MBR, membrane technology. Mainly, actually, I'm going to focus in the basic process, like design, what kind of membrane and what's the common design of the membrane bioreactor and how this membrane bioreactor can be operated. And in this session, I'm going to cover like brief historic background about the MBR and how the idea of MBR started, and then I'll show some main membrane separation processes used in MBR. Later, I'll show some configuration, whether like MBR configuration or membrane configuration, and the general concept. When you work with the MBR, you will use like different terminology and concepts. Later also, I'll show some the common companies working on MBR, how you can access that companies and for information or the products. And also I'll show some application currently for MBR, and definitely MBR, when you work with the MBR, you will face some challenge like membrane falling and other challenges, and I'll introduce some of them in this session. Actually, historically, the idea of wastewater treatment started with the activated sludge process. Usually with the municipal wastewater or industrial wastewater, pre-treated or treated by activated sludge process. And this process usually using aeration tank. The aeration tank usually will promote the microbial community to degrade the organic materials in the wastewater, whatever the source of the wastewater. And then after the degradation of the pollutant in the aeration tank will be moved to the second tank, called secondary clarifier. And in the secondary clarifier, mainly in this step for the settling of the flux and the pre-treated materials. And after settling, we can get out the effluent or the supernatant out when the settling material will be recycled back again, because it's containing the microorganisms that can be used to degrade the material again. And actually this material used effectively and currently actually in use, but facing like some drawbacks. One of the main like drawbacks for the activated sludge process, because when you moving the material to the settling tank, sometimes the material will make like foam and will not settle like totally. So when discharging the effluent will be containing some biomass, and mainly the microbial biomass. And that actually will result in like low grade effluent, and that effluent cannot be reused, for example, in irrigation, or for example, in other industry like pulp and paper industry can reuse the effluent. And this one is not good in quality to be reused. And also when wasting the microorganism also will affect the performance again, because you have to recycle it back here to do the job again and again. And when you wasting call it the wash out of the biomass, when the wash out happening, this will affect the performance of the system. And because of this like drawbacks, the people started to think how we can solve this issue. And then the idea of membrane technology started. And mainly actually the idea started using the same activated sludge process and incorporating the membrane filtration process with it. And this idea actually started in late 1960s after the commercialization of the microfiltration membrane and ultrafiltration membrane, and the first MBR actually was developed and designed by the Oliver Incorporation. and mainly actually combining the activated sludge process with cross-flow membrane filtration system, mainly using cross-flow membrane filtration system because this one will use tangential flow. That means we can reduce the membrane falling. After that, actually, a lot of the development and work has been done in this area. For example, from 1969, an ultrafiltration membrane was used for wastewater treatment, and later actually tank was developed for membrane filtration in 1978, and the first pilot scale anaerobic membrane bioreactor was constructed in South Africa in 1987. In 1990s, actually, a lot of work has been done in Japan. And actually, if you know the Kubota biogas, MBR company actually did a lot of work in this area, around 10 years of research in this area. After 2000, actually, a lot of dissemination and publication has been published out in this area, and a lot of work has been done in membrane technology. And actually, I didn't check. I don't know if everyone like hearing me clearly. Hello?
Yes.
Okay, good.
Yeah.
That's good. Yes, I'm checking if like everyone's seeing and hearing, like
Yeah.
hearing
Yeah.
me. Like,
We,
yeah, okay.
yeah.
Yeah, that's great. Yeah.
Yeah. We see your presentations here. Yeah.
Okay, that's great. Actually, as brief like introduction and comparing between the activated sludge process compared with membrane bioreactor, uh, like as has been like shown before, in SB, like only we use like settling using gravity to settle the pretreated or the degraded materials there, and then the settling cannot be in good condition, and so we can wash out some material out. That is one of the main like drawbacks, and also the fluent quality. When we use MBR, actually, because the membrane can reject back all the solid while getting clear permeate for reuse, can be reused in different like purposes. And also for the because when eliminating the secondary clarifier in the activated sludge process, so we can like we can save like some space, will be like more compact system MBR. And actually, the more interestingly, when we're using MBR, we can decouple or separate the solid retention time from the HRT, hydraulic retention time. When using activated slide process, usually the HRT will be equal to solid retention time. But when we're using MBR, so we can separate them. Everyone can work like differently. For example, we can operate in 40 days solid retention time, and we can operate in like few days hydraulic retention time. Mainly is because we can separate the solid from the liquid. We can take the liquid out through the membrane while leaving the solid inside, and then usually we'll waste the solid from the time to time, and the amount wasted will be calculated for how much is the solid retention time. And this actually is the main benefit. So when we have like liquid effluent with high strength, so we can benefit from it. So we can pump the water as quick as possible out while maintaining the solid inside. In membrane bioreactor technology, actually, commonly there are two types of membrane used, membrane filtration process used, microfiltration and ultrafiltration membrane. Actually, in place, we have a lot of different types of the membrane separation processes like reverse osmosis, nanofiltration, evaporation, but it's not like used in MBR. The common membrane used in MBR is microfiltration and ultrafiltration membrane processes. These two membrane processes actually almost the main difference between them is the pore size. For the ultrafiltration membrane, little bit like tight pore size compared with the ultra filtration, compared with the microfiltration membrane. The pore size for the ultrafiltration could be less than or around 1 nanometer to 100 nanometer, compared with the ultra microfiltration can reach to like 10,000 nanometers. So like when the bore is so tight, and then you need to apply higher pressure to pump the liquid out of the membrane. So ultrafiltration has slightly higher pressure, like to get the fluid out of the membrane. So when you have higher pressure, also you need the thickness of the membrane should be a little bit higher or bigger, because you need the membrane to be strong enough to withstand for the higher pressure. As the two mechanism of the separation in two of them like sieving mechanism, as shown here in this animated diagram. You need to push through the pressure, the liquid out, and for example, ultrafiltration membrane can reject most of the material like particles, colloids, bacteria, and also protein and polysaccharide. However, when the polysaccharide reduced to monomer sugar can pass through the ultrafiltration membrane, and also amino acid can pass, and also if we have like monovalent or multivalent ions also can pass through the membrane because it's small in size, plus the water definitely can pass through the membrane. Uh, uh, the main actually membrane module configuration used here, flat sheet membrane or tubular membrane, and also hollow fiber membrane. This like the common membrane modules used in both of them, microfiltration and ultrafiltration. Later, actually, we will talk a little bit in details about this configuration and how can be configured. The material, also the common material used, polymeric membrane and ceramic membrane in both of them. I have here a like showing the pore size, because this pore size, when we're talking about nanometer, will be so small in size. When using ACM, like scanning electron microscopy, you can see this pore actually. This I think this one for the fabricated membrane, and the other one actually just recently we published paper about membrane falling characterization and residual falling evaluation. So when you operate the membrane, actually before the operation, you can see the pore when using ACM, but later actually due to falling, most of the small pores can be like constructed or clogged by the falling. And this one only you can see it by the ACM images or other tools. In this slide, we're going to talk a little bit about the main configuration used in MBR. These two main configuration use submerged membrane bioreactor, and in this one, actually, the membrane module like inserted inside the digester. So the membrane inside the digester, and then by suction you can get the fluid out of the membrane. And the second one called side stream membrane or external membrane configuration, MBR configuration. And here, mainly the membrane module will be placed outside the reactor tank, and then the liquid will be we use pump here like to pump the liquid uh, outside or inside the membrane tank. Sorry, the reactor tank. And here is like two main configuration, submerged membrane or immerse, and side stream or external MBR. Actually, I have question for you guys. What do you think, like, what are the main advantage of using submerged membrane bioreactor over a side stream membrane bioreactor or vice versa? Actually, each of them has its own advantage and drawbacks. And here I'll show you like some just listed key point for that. When we use like submerged membrane, when membrane is submerged inside the reactor, actually definitely the design will be simpler like design, because we have one unit and everything like compact. And also we can reduce the energy because we have when we when you have the external membrane, you need to recycle back. When recycling the water back, you need to use the pumps and the piping that we can add more energy to the system. And I said before also it's compact design because one unit and also low capital cost because just you have one unit instead of like two different units of the system. And also actually has some drawbacks. When you have membrane immersed inside the system, actually the surface area of the membrane will be reduced because you have it's like governed by the reactor size. You have to design the module based on the reactor size. So when you put the module inside, you have definitely a small surface area. When you have a small surface area, you will get less flux. And also when you put the module inside the system also can be damaged because a lot of the obstacle and stuff inside the system will be designed there. And also when you need to actually usually the membrane will be fault more often. So if you need to clean the membrane and also you will face some challenge. Most likely you need to get the membrane out and then clean the membrane. And actually when you use the anaerobic system, it will be so hard because that system should be maintained without oxygen. When opening the system, that means you have some air getting inside, that means disrupting the microorganism. So you will face some challenge. And also when you need to scale the system when using submerged membrane module, you will face some challenge because you have fixed volume of the reactor. And if you need to increase the membrane module size, it's hard because it will not fit inside. So you have to build maybe new reactors and then you can fit a new membrane module. Actually, this one is not like the case in the external membrane because you have some flexibility because membrane is outside, you can make it bigger or smaller because it's not controlled by the reactor size. And also we can apply higher pressure when we put the membrane outside, that higher effluent or flux compared with putting the membrane inside, that you have to consider a lot of stuff here because if you apply more pressure, you can make leak in the system and then you have to fix that again and that rising in some challenges. And also easy cleaning process because external, so you can open it at any time because no worry about introducing some air to the system or other problem. You can open the external one and do the maintenance and cleaning. However, actually this one also has some drawbacks because when using external, you need to use more pumps and piping, and that can increase the complexity and also can increase the energy consumption. And also if you have tight space, that will be the issue because you need extra space to put the extra like pumps and connection for the module. Like to select between these two membrane bioreactor configuration actually depends on different factors. For example, if you care about the energy efficiencies, I think you need to go for some membrane because it will be one unit and less like capital cost and also less like pumping and piping for that. But if you care about ease of maintenance, like to clean the membrane and to clean the fouling, I think external membrane will be the right choice for you. And also the in terms of the space constraints, if you have like tight place, I think you need to consider some membrane rather than using the external one because you need like a wider space to fit the two systems. And also in terms of cost consideration, actually, I believe the submerged system can be like a little bit because you have just one unit compared with the two-unit system. In terms of process control, I think external system will be better because easy of operation and controlling all the parameters. After we talked about the MBR configuration, and right now this is the membrane configuration. Actually, also the membrane has different configurations. The main configuration used in MBR actually three configuration: flat sheet, and tubular membrane, and hollow fiber. Actually, we have other configuration like spiral wound membrane or capillary membrane, but actually it's not common in MBR. These are the three common configuration of the membrane used in MBR, and we're gonna to show like little details about each of them. For the flat sheet configuration, usually will be just like thin flat sheet membrane, and actually usually this will be constructed in module size, in module form, and actually it has like some also advantage such a configuration because the durability is high for the membrane, and also for the use, a lot of it like used for wastewater application. Compared with the hollow fiber membrane, usually actually be just straw-like fiber with hollow opening in the center. And actually, this one ideal for the large scale wastewater. Actually, this one we have bigger surface area compared with flat sheet one because we have different bundles. Each bundle actually containing a lot of pores around. That means you have compact and small module, but actually the surface area and the flux can be higher for this one. And when we go to the tubular or multi-tubular membrane, here is like containing like different channels and actually so durable, this one, and rigid membrane, and usually used when you have like wastewater with high solid colloids, you can use it, and also when the viscosity is high, you can use tubular membrane. Actually, I have short video here, just around 1 to 2 minutes. I need to show you how the flat sheet. Actually, this one from the Kubota company in Japan, constructing a flat sheet membrane externally.
So is there any sound, Alnour, or just
Actually, no sound, just music.
okay? All
Yeah,
right.
I can increase it. Yeah, you hear it?
Not really.
Okay,
But
yeah,
that's fine.
actually, just I need to show just the configuration. Okay,
Okay,
here
sure.
actually the configuration, the membrane unit will be configured from different materials, supporting the frame, and then the membrane will be inside. Later will look like this, because this the membrane and supporting material and the frame. The unit will be like this, and there can be configured in module. All of them can be as module, and you can put actually extra module also. You can, yeah, you can add more modules, and then this one actually used externally. This is the reactor tank, and then here you have the membrane tank, and then later you can get clear effluent for reuse. And this is actually in application right now with Kubota membrane company. Okay. After we talked about the membrane bioreactor configuration and membrane separation configuration, here actually this is a common material used for manufacturing of the membrane. This is like the two main materials used: organic coated polymeric membrane or ceramic membrane. For polymeric material, actually different sort of polymeric material can be used as polyether sulfane and poly tetra polytetra fluoroethylene and polyphenylidene fluoride membrane. Actually, I work with polyphenylidene fluoride membrane a lot during my PhD, and I did a lot of characterization about PVDF membrane. And also other sort of the membrane used is polyether sulfane membrane and polypropylene membrane also used a lot right now in the market, and polysulfane membrane. Uh, For the ceramic membrane, a lot of the material also used like aluminum and silicon carbide and zirconia and also other type of material, pyrophyllite membrane materials. Sorry guys, just drink a little water.
Okay, no worry. Take your time.
Okay, actually this is the sort of the membrane material used commonly just characterized as ceramic membrane or polymeric membranes. Actually, each one has its actual advantage and drawbacks. Using polymeric membrane, easy to configure and however, but can be like is not durable enough when applied under certain conditions compared with ceramic membrane. It's more durable and can withstand actually harsh cleaning condition. Because when the membrane is fault, sometimes we need to use some cleaning steps. Could be physical cleaning just to clean the membrane module using a sponge or other sort of cleaning way, call it physical cleaning. Sometimes the physical cleaning cannot remove some of the foulant, so we need to apply chemical cleaning. For example, to remove the organic material, usually we apply sodium hypochlorite solution, certain concentration, and then we can degrade the organic material built on the membrane. And if actually at each time we have to test this, we test call it the recovery percent or the permeability recovery. When you clean the membrane physically, we need to apply call it flux. You need to test the flux. Okay, the flux is getting back against as the original membrane or not. If not, you need to go to the second step of the cleaning. First physical and then chemical cleaning using, for example, sodium hypochlorite to degrade the organic material. Also will test the recovery, if good or not. The second stage, if not good, you need to use, for example, citric acid to remove the inorganic material from the membrane. So when we work with ceramic membrane, so no worry, we can use like strong chemical to degrade this material, but when we work with polymeric membrane, it's hard to apply high concentrated solution to clean the membrane from the falling materials. Here like this, some picture just showing the polymeric membranes. And this one flat, actually this flat sheet membrane, and then just you can cut whatever you need, and then you will construct your membrane module. Actually, we have this. I work with this membrane flat sheet a lot also. Just you will get the flat sheet, and then you will design your membrane module. You need to get the supporting materials and then the protective material, and then the membrane will be inside. And you will design your membrane actually based on your reactor size. Will be like two sides, and then you will calculate the surface area from the two sides of the module. And then based on that, you will calculate your flux and your filtration stuff. The second sort of the membrane here is the ceramic membrane. Also, this cross section of the ceramic membrane, actually a lot also of the supporting material, and then intermediate layer, and then you will get the thin layer here, this is as membrane. But actually the outside stuff, all of it just supporting material. Exactly when you construct the flat sheet, also you need to put a lot of support, otherwise you will damage the membrane, mainly when you immerse the membrane inside the reactor. And ceramic membrane can be also like multi-channel or multi-tubular membrane, as shown in this picture, or can be like flat sheet ceramic membrane, and can be also hollow fiber membrane. Actually, polymeric membrane also can be in sort of the hollow fiber. Actually, we work with the Xenon company before, and we work with the hollow fiber polymeric membrane to see the performance of it for sometimes. As mentioned before, the ceramic membrane actually constructed of different sort of the material can be like aluminum oxide, can be silicon carbide, or titanium dioxide, or conium dioxide also. Some of the material can be used to build or to manufacture the ceramic membrane. Actually, in the second section here, I'm going just to introduce some concept and the terminology commonly you will hear when you work with the MBR, brain bioreactors. We're going to talk actually just I'm showing here listing some of them, but we're going to talk to focus on some of them in details later. For example, membrane characteristic, and then here mainly we talk about membrane pores. First, you need to do some characterizing, because initial characterization of the feed water to see the your material, and then based on that you will select the pore size of the membrane, and also you need to consider like other factors like the surface charge of the membrane and the hydrophilicity and hydrophobicity of the membrane and contact angle, a lot of stuff you can do for the membrane to characterize the membrane based on your on the feed you need to handle with membrane. And also you will hear a lot about the flux. Actually, when we're working with MBR, actually, we have two different terminology. Terminology is related to membrane and others terminology related to the reactors. This section is mainly related to the membrane. So later I'll introduce some terminology related to the reactors instead of the membrane. And also you will hear about the flux and the flux recovery and the critical flux, which will actually the people actually develop the flux limits that you can consider when you operating MBR, because beyond the critical flux, you can get a lot of falling because the transmembrane pressure will be increased and will face a lot of, you have to clean the membrane. And below the critical flux, you can get falling, but for longer time of operation. And also you will hear about transmembrane pressures, and that can be used as indicator of falling and build up of the material on the membrane surface. And commonly, you will work with the permeability, because you need to test the permeability before the operation of the membrane to see how the, under this condition, applied مثلا pressure and other like operating condition to see the flux, and later after operating the membrane to see the flux. Because if you need to do, for example, the cleaning and maintenance, you need to compare the permeability before and after the operation. And definitely you will work about membrane falling. And this point, actually, we're going to show some what's up membrane falling and how can be cleaned later. And the maintenance or the cleaning steps. When like of the main terminally or the for the membrane module, actually membrane flux, and mainly actually the flux is the how amount, how much like permeate can be permeated through the membrane per unit of the membrane. So we have membrane module, and then how much like liquid can be pumped out through the membrane. This is called the membrane flux. And usually just we calculate it as, for example, liter per hour per square meter of the membrane, and mainly depend on the membrane surface area at like volume per a certain time per like surface area of the membrane. And usually actually this terminology used instead of liter per hour per square meter will be LMH. This commonly people like use when you're operating MBR, and you can hear it more often. The transmembrane pressure actually mainly is the pressure like region differences between the feed water side and the permeate side. The difference of this pressure usually call it transmembrane pressure. Usually actually transmembrane pressure with the flux will be combined, because the TMB usually will drive the membrane flux. So we can like construct the relationship between them will be the flux will at certain like temperature can be calculated as a sort of the TMB divided by the a total resistance and the viscosity of the effluent treated by the membrane. And actually, we use this terminology mainly like to see the when we're talking about the membrane performance. Usually, we use as this terminology and equation to calculate to see the performance of the membrane. And when we're talking about the total resistance, actually, when we're talking about falling, actually, we have different sort of the resistance. Uh, total resistance, sorry. A total resistance actually can be a combination of the membrane resistance plus falling and plus cake layer resistance. And membrane falling later can be actually divided into different sort of falling. Can be uh, inorganic falling, organic falling, and call it permanent falling or reversible falling. We need to consider that when working with membrane bioreactor. And the membrane falling actually this is called inherent membrane resistance. Sorry, not for the membrane resistance, the RM or membrane resistance is called inherent membrane resistance, and this is due to the membrane material. This will be just there. And the second one actually resulting of the building of the material inside the membrane pores. So making membrane pore tight and then making some resistance called falling resistance. And other people, as I said, usually dividing this one to different sort of the falling and the cake layer. And actually, when the TMB will increase during the operation, that means the cake layer most likely will build in the membrane surface. And this mainly depends on the type of the wastewater used and the characteristic of the wastewater handled with the membrane. Uh, Above all, actually, we need to take in consideration the viscosity of the material because the temperature can be like different from the operation to operation and from the climate to climate. So usually we need to unify the condition. For example, to compare the permeability across different like condition, we need to normalize, call it normalized flux or uh, standardized like temperature flux. Usually, commonly we measure the permeability at 20 degrees Celsius, so can be compared like across different operation conditions. Because, for example, if you tested your permeability at room temperature, and then the viscosity at room temperature, you need to apply that viscosity, and later you need to normalize it to the 20 degrees Celsius to be comparable with the other operation conditions. It's like more often you will hear it when you're comparing the permeability of the membrane under different conditions, for example, solid retention time, hydraulic retention time, or organic loading rate. After we talk a little bit about the concept related to the membrane, and here we have some concept related to the actually the reactor, the digester. And more often you will hear about the operating condition, solid retention time, mainly will be like how long the solid will be remain inside the reactors, and also the organic loading rate, how much like organic amount will be loaded to the system under a certain time, and also based on the reactor volume. As a second term, commonly like you will face with this application, the hydraulic retention time, and as I said before, MBR actually decoupling this solid retention time. We will calculate the solid retention time separately from the hydraulic retention time. But when you're using this activated sludge process, the solid retention time actually will be equal to the solid hydraulic retention time, HRT, because no way to separate them in activated sludge process. But in the MBR will be decoupled. You can make longer solid retention time, shorter HRT. And here I'll show you a little like simple way to calculate the such a concept. For example, to calculate the HRT, if you have reactor with 120,000 cubic meter, and you like pumping inside around like 3,000 cubic meter of the wastewater per day, simply you will divide the reactor volume by the effluent getting inside the reactor. and then you will measure your HRT around like 40 days. We can make it, for example, 40 days for HRT, but we can make it like 60 days for the solid retention time. We can separate them. And actually, when working with MBR, the HRT can be so short, can be actually hours. Instead of days, can be hours, but the solid retention time can be a few days. That's the main advantage of using MBR. And actually, for the organic loading rate, usually will be calculated like based on the organic material added to the system. This organic material can be measured in terms of the volatile solid, or can be measured in terms of the COD or BOD, chemical oxygen demand, or the biological oxygen demand. We can calculate it based on that to see how much is the organic loading rate for the system, because actually the organic loading rate can affect the performance. For example, higher organic loading rate can deteriorate the performance because can lead to the build-up of the acid in the system. When the acid will increase, as the reactor will be upset, and most likely can lead to the reactor failure. So you need to consider that, and you need to consider also what sort of the wastewater you are handling. And then based on that, you need to select all your design, your parameters, for example, organic loading rate and HRT. And also HRT can affect also the system performance, so you need to consider that. For example, if we have like feed rate like 500 kilogram per day, we add it to the system, and we have substrate with volatile solid content around 20% or less. Then just we can calculate how much organic loading rate we have, just dividing the amount added, multiplied by the concentration, and divided by the reactor volume. Then we can get how much organic loading rate. And usually we term it kilos of like VS or kilos of COD per cubic meter per day. Cubic meter in terms of the reactor size and in terms of the time. And actually, when operating the reactors, you need also to calculate the degradation of the VS or COD. And usually, yes, we use the differences between the material, actually, when you add in the feed to measure your COD or your VS, or volatile solid, in your feed. And then after the digestion, you need to measure the material in the digestate, and then you will get the differences between them to get the solid reduction percent. Actually, can be calculated for the total solid, also can be calculated for the total suspended solid, whatever like the term used to evaluate your reactor performance in terms of the organic matter degradation. For example, if we have like feed with VS 60%, and we have the digestate, we measure the VS around 40%, then just we get the simply just we can do the calculation to get how much degradation efficiency we achieve under that process. And in the other way, yes, we can calculate it by the percentage differences between them also to get how much material like degraded or the percentage decrease of the materials. The reduction percent actually also depend on the substrates. Some like substrate you can get higher degradation efficiency. It could be like 60, 65. Some material like lignocellulosic material, usually the degradation efficiency will be a little bit lower, around 50 or 43, around that number. This is in terms of the volatile solid. Actually, however, when using the membrane technology, usually we reject most of the solid inside, and the solid can get more time to be degraded while getting the effluent out. And usually the permeate will be clear permeate, so we'll measure the concentration of the permeate in terms of the COD, and then we compare it with the concentration of the feed. will actually the degradation efficiency of the COD will be so high, can reach around 98% or so. Because the membrane usually will reject all the solid out, and that's what and actually the membrane is using the waste of the sludge. When working with the activated sludge process, we can generate a lot of the solid, and that you need to handle and to manage that waste or sludge. But when working with MBR, because the solid will be rejected inside, and then we can reduce the footprint of the MBR because you're getting like clear permeate for reuse. Yeah, actually, just I'm showing just by way of example, not as limitation of the companies working on the membrane bioreactors. In Canada, actually, Xenon working with the membrane and following a lot of membrane system, and US filter working in Australia and United States. And the famous one is Kubota, like corporation in Japan, is building actually building anaerobic membrane bioreactors. You can get like different configuration or size ready, just you need to install it and you can use it. And also for testing in the laboratory scale, you can get a reactor from the Kubota, Japan, MBR, mainly working anaerobic membrane bioreactors, and also Toray industry in Japan also. Mitsubishi manufacturing some membrane sort of the membrane, and GE water and process technology. This company right now is part of the Swiss water technology and solution, actually working in the United States and in Canada. We work with them also. We test some membrane performance for them with hollow fiber polymeric membrane. Right now, also, I think working here in the United States with different universities, testing different membrane and reactor sizes. And in the United States, actually, also the famous one is the Viola water technology. It's working with a different sort of the technology and membrane technology. And in Singapore, we start so famous technology, Singapore for the membrane technology, Memstar. Actually, just this as example for the companies working on the MBR, but it's not like as limitation for these companies, because can be way higher, need way more than the listed number. Actually, membrane right now is like developing rapidly over the globe. I know this actually data a little bit old, showing the trend up to 2016. But actually, the MBR developing like more rapidly, and this data actually just showing the dissemination of the publication and patterns, and mainly on the like super large MBR scales right now in operation, increasing like rapidly after actually mainly after the 2008, as this is an inflation year, increased to start to increase. And actually because a lot of the, as I mentioned before, a lot of the publication and development happened after 2000. And people start to understand the membrane configuration and how to operate the membrane, because it's tricky to operate the membrane, and you need to be trained well to operate and to do the maintenance and the falling cleaning and installing the system. Compared with working with the activated slot process, with a simple process, and it's not much challenging. And usually will be operated that one in aerobic condition, activated slot process. So it's not hard to operate the anaerobic MBR, because you need to be trained and to maintain the performance, and you need to be trained to use what sort of the cleaning you need to apply. And actually some companies also providing the cleaning procedure for the membrane. When you get the membrane, and then you will get the cleaning procedure. Could be physical and chemical cleaning or combination, and different of the cleaning solution actually can be used depending on the membrane and membrane material and characteristics. But the more common used solution, sodium hypochlorite and citric acid, and this is actually used for the organic material and organic materials and for the inorganic materials. In terms of the applications, sorry, to get just a little water. Sorry, guys.
No worries. Take your time, Alnour.
In terms of the application, actually, not much left to say. I think I use a lot of time. I'm trying to go fast, but still, this making this process short. In terms of the applications, MBR actually used commonly in the municipal wastewater treatment everywhere in the world, because the municipalities usually using activated sludge process right now, like to get effluent, because to get clear effluent for irrigation or for other application, so you can apply the MBR instead of using activated sludge process or other conventional system. Actually, also can be used in the industrial wastewater treatment. In Canada, actually, I visited some pulping companies for resolute companies using MBR. Actually, using direct filtration and using MBR as a digester to produce biogas, and that biogas can be used to generate energy. And also, you get clear permeate, actually, almost like look like water permeate, and that can be reused again in the bulbing process. Because in the bulbing, we use a lot of water to do the bulbing. So instead of like discharging that water out and making, and actually a lot of restriction and limitation to discharge the effluent out, it's not possible. So the government actually day by day here in North America putting some restriction to discharge the effluent out. So each bulbing company has the wastewater treatment facility. Could be conventional or MBR. And MBR right now just started to be like installed because you can reuse the water again and again. And actually, in the like the shift towards the biorefineries also encourage the people to use the MBR because you can get effluent and this water can be recycled back again to the system. And also you can get digestate. Digestate can be used as fertilizer or other applications. And also the system can be used for the leachate, like from the landfill. If you have like a lot of liquid getting out from the solid, that can be collected, and then because usually will be like high strength wastewater, can be used in MBR to produce like biogas, and then getting the rest of it as clear, permeate, and less solid generation. Because this will be contaminated if run out to the water bodies, will make a lot of contamination. So you need to collect it, and then you can use MBR to treat the leachate. And usually, actually, when working with anaerobic MBR, if you have high strength wastewater is good. If you water containing some organics, because you can generate energy, and that energy can offset the cost of the operation. Because when operating MBR, you need like some energy. So if you instead of working as aerobic condition, you can operate it in an aerobic condition. So you can generate some energy as methane, and that can offset the operation of the system and reducing the cost. And a lot of installation also in Europe for the food processing wastewater and pharmaceutical wastewater was MBR. Actually, I noticed like in Scandinavian countries, a lot of installation for the MBR compared with North America. A lot of installation used there. And actually, MBR supporting even some cities like with energy, because you're getting methane, and that methane can be used for heat or other application as energy. Definitely, like working with the MBR or the activated sludge process, you have some challenge. But the main challenge when operating MBR, the maintenance and cleaning of the membrane fouling. Membrane fouling simply actually is the build up of the material of the membrane surface or inside the membrane pores. That can reduce the permeability or the flux of the membrane. So we have to clean it more often, and you have to schedule, call it the maintenance cleaning, from time to time, could be monthly, could be 3 weeks, to maintain your flux. Because if you then maintain your flux, usually you need to apply more pressure. Applying more pressure, that means using more energy. Using more energy, you're wasting a lot of money. So cleaning the membrane, opening the pores, that means the flow rate of the flux will be maintained. And then while you maintaining also your low cost of the energy, because when the material will build on the membrane to push the liquid out, you need to apply high pressure. High pressure, that means high energy. Uh, Actually, also some costs will be associated with MBR compared with the activated sludge process, because you need to buy mainly the capital cost for the membrane module, because this will increase also the operation and energy consumption. Shortly, we'll talk about how to mitigate or prevent the brain falling. So when we're working with MBRs, sometimes we need to call it scoring or sparging the membrane. Actually, we recycle the produced biogas. Actually, I work with anaerobic membrane bioreactor, recycling the biogas in the bottom of the membrane module. That bubble can remove the material, mainly the cake layer that built on the membrane surface out, and then you can maintain your flux for longer time. Then you can reduce the, the period of the doing the cleaning. But when you're using, if you need to recycle the gas in the bottom of the system to score the module, membrane module, that means you need to put extra pumps. That extra pumps, that means you need to use more energy. So it can be associated by the energy consumption. In terms of the sludge management, actually, it's not that hard as the activated sludge process, because actually the footprint of this process is slow. It's little, it's not much, and most likely this sludge used as like state as fertilizer, and it depends on the what kind of the material like handled with the system, and also the complexity of the operation compared with, actually this relative, because compared to the activated slide process, a little bit complex, because you need to do some maintenance and stuff, and you need to be trained to operate the membrane bioreactors. In this section, I'll show you what is because this is the main challenge actually in the MBR. What is the membrane falling? As I said before, it's the accumulation of the unwanted material on the surface or within the pores of the membrane, which reduces the performance. I mean, mainly the flux. The flux will be less. And when actually, usually we operate the membrane, call it under constant flux or under constant pressure. When you operate under constant flux to maintain your flux, that means the transmembrane pressure will increase with the build-up of the material on the membrane surface. So you need to do to understand the membrane falling, and you need to do your cleaning maintenance for the system. And a lot of work and publication, actually, we published several papers related to the membrane falling characterization, membrane falling cleaning. And this actually, I think from our paper 2008, published in Bioresource Technology, we showed how we can characterize or categorize the membrane falling. Can be like pore blocking. At the beginning, will build on the pores. With the time, also membrane can absorb some materials with the operating time, or can be as cake layer, be like layers throughout the membrane surface, and also can be gel layer. And these differences depend on the feed characteristics of the treated like industrial wastewater or municipal wastewater. Can vary, or you can get actually combination between the cake layer and gel layer, because based on the materials. And like further also falling can be categorized based on the source of the falling. Could be like biofalling, because mainly from the microorganism in the system. or can be a particulate falling with particle material containing inside the effluent or the wastewater, and could be actually inorganic falling if the wastewater containing some inorganic material, so definitely can result in inorganic falling. Or could be like organic falling, mainly organic others could be protein or others uh, polysaccharide can also stick on the membrane and making inorganic membrane falling. Different factor actually contributing to the falling, actually the wastewater, the feed water or the wastewater quality, for example, the turbidity or organic content inside the wastewater or concentration, and the microbial contaminant also can contribute somehow for the biofouling and operating condition. Like for process design, you need to operate actually your brain under certain condition in terms of the HRT, in terms of the solid retention time. And actually we notice like when the solid retention time is longer, I mean old in age, a lot of material will be degraded and only the leftover there will be inorganic material, be inorganic falling with the time of the longer digestion. Also, when you're operating with higher organic loading rates, that means a lot of organic uh, getting inside the reactor that can build on the reactors also and making some challenge. So you need to figure your organic loading rate and also your flux. More importantly, you need to operate under constant flux or constant TMP. Then you can operate differently. You should be below the critical flux. Otherwise, you will increase your TMP and you will do repeated cleaning process. Using chemical and stuff also associated with cost and labor stuff. And also you need to select your material, membrane material. As I said before, like 10 of the pore size, I think I work most repeatedly with microfiltration membrane because actually compared with ultrafiltration membrane because the pore size is bigger and easier. For example, to meet the the standard of each like wastewater characteristic, for example, in Canada, working with microfiltration membrane is fine because we will meet the standard of the wastewater discharge as effluent. So working with microfiltration, that means the pore size a little bit bigger, that no need to apply high pressure, that means we're saving some cost for energy and other stuff. So we need to select the material in terms of the like charge, so negative charge membrane, and also the hydrophobicity. We need to consider such a characteristic of the membrane when you're selecting your membrane for the operation. And actually, some people doing some like pre-treatment, pre-treating the influent or wastewater. To reduce the falling, some people will do like coagulation to coagulate the material. That means you can reduce the, because when the material in the big size frogs, we can reduce actually the falling. This material cannot get inside the small pores, cannot like penetrate inside and then block the pores. Actually, I'm seeing some questions. I think later I'll go through them. Almost I finished, but yeah, I
I
saw
think
some.
you can finish it first, probably for your
Yeah,
presentations.
exactly. But
Go
almost
together.
there. We can finish
Yeah,
and then I
sure.
think only around 2 or 3 slides left.
Sure. Yeah, take your time.
Yeah, and then we can go through the question. I said some like companies will use sometimes like just using a sieve to get some like big particles out that can damage the brain, and some people using filtration to reduce some loading of the material or the coagulation actually to make like frogs and stuff to reduce the falling because you're making big particles that cannot get inside the pores, cannot constricting or blockage in the pore. Actually, also like a lot of strategies has been used to mitigate the brain falling. Also, we publish actually, I don't know, 4 3 papers about strategies to mitigate the membrane falling. If someone interested, I can just list some of them later. Beside membrane cleaning, actually we can mitigate the falling. That means we can manage our operating condition, as I said before, under the membrane critical flux, not operating the high TMP, transmembrane pressure, so we can maintain the flux for longer time. As I mentioned before, we can pre-treat the wastewater before like pumping the water to the reactors. And also like selecting the right brain characteristic also for your process can reduce the falling problem. This diagram is actually showing uh, for the new membrane actually without falling, then you will see some material will be like penetrated inside the pores, and it depends on the size of the materials. Actually, the bigger size can be outside, like this one, making a stuff like a cake in the membrane surface, and some of them, the small particle can be penetrated. So usually we'll get the membrane out, then we're doing physical cleaning, can remove some of the material, and then some of it will remain. We'll do chemical cleaning. Chemical cleaning can be as using base or acid to clean the material. Actually, depend on the materials. Usually, actually, when operating in the external MBR, some people will do like call it back washing or back use of the membrane, just pushing the material back of the membrane, applying uh, back flux again that can push some material out and opening the pores of the membrane. But it's when operating in the submerged membrane, I think you need to get the module out and then to do the cleaning and maintenance of the membranes. Since actually I finished my presentation, actually most of this work from we published book chapter in 2020 about anaerobic membrane bioreactor basic process design and operation. Actually, this is part of the nice book actually in current development in biotechnology and bioengineering, published by Ashok Bandi. He was the editor-in-chief of bioresource technology. And this book actually right now outside there. If one interested for more details can go just to access it and read about the process, basic process design and operation of MBR. Actually, a lot of nice stuff there. Actually, so far, I think I can say thank you to you, and I can go through the question. Actually, I saw some of the students
Yeah,
posting questions there. I can
yeah,
go,
yeah. There
or
are some
body, just
questions
you can read,
here.
you, you can read one
Um,
by one, and then I can
sure.
answer them.
I think probably we can call them now. So we have Gerardo
Yeah,
Moscoso. Yes, are you here, Gerardo? Uh,
Yes,
is
I am.
oh yeah, that's
yeah,
Gerardo. So probably it's gonna be good, like you have interactions with the speaker. So
okay.
if you want to ask directly, go ahead.
Thank you so much. Good evening from Ecuador country.
Oh,
First
Oh,
of
you're
all,
welcome,
I want
welcome.
to, excuse me?
That's great. Yeah, go ahead.
Okay,
Yeah,
go ahead.
yeah.
Good evening from Ecuador country. First of all, I want to thank you for this great lecture. It is so interesting. I would like to make an ask,
Thank you. Thank
Doctor.
you.
What do you consider to be the main technical and economic challenge for large-scale implementation of membrane bioreactors in the industry? Additionally, what recent advancement might help us overcome these limitations?
Okay, that's good question. Actually, good questions. Uh, Actually, the main challenge in terms of the economy for the implementing MBR for the large scale Uh, Actually, it's the membrane falling. Membrane falling actually contributing bigger portion for the cost because this one is not like one time. You need to do like repeatedly the cleaning. Sometimes this cleaning can lead to the damage or degradation of the membrane. So we name it membrane lifespan. That means we need the membrane is almost done. We need to put new module. When you adding new modules, that means increasing the cost. This is the main challenge. So to overcome this challenge, actually we need to develop membrane with modified like surface. That membrane can reject most of the material. Most of the material cannot stick on the membrane surface. Because when like all of them like hydrophobic material or depend on the surface charge, we definitely will get some material stick on the surface on the membrane. So if we manage to modify the membrane surface, can reject most of the particles out, that development can make big change in the MBR.
Okay.
I think, yeah.
That's it.
Great. Thank you.
Yeah,
Thank you
yeah.
so much. It
Yeah, you're
is
welcome.
awesome.
Thank you, Gerardo, for the question.
Thank you. Thank you from Ecuador.
Yeah, from Ecuador.
It's a pleasure to meet you.
Nice to meet you too.
All right, we also have another participants here, another questions from participants. Ibu Indira. Bu Indira is our lecturers in Department of Food Technology, and I think she's here. Is Bu Indira here or not?
Yes, halo Kak Budi. Apa
Halo Bu
kabar?
Indira. Baik-baik. How are you doing? Good.
Alhamdulillah. Hi, Dr. Bokhary. Nice
Hi,
to meet
Indira.
you.
Nice to meet you too.
It's a great lecture for me and
Thank you. Thank you.
new knowledge for me because I just use the water from I just use the what is the water after the process. So relating to my question, I would like to ask about the safety
Yeah,
level of wastewater that has been what is filtered using the MBR method, and then is it possible to use that recycled water in food processing? Because in Indonesia, the water that produced after the recycling is not recommended in food processing. Thank you.
Okay, thank you.
You're welcome. Actually, for recycling of the, I mean the effluent for reuse when using MBR, I think is possible because actually, for example, if you use ultrafiltration membrane, actually almost you can. Actually, I have picture for my reactor I operated in Canada. Almost we can get clear water like this actually, clear permeate, totally clear permeate. Sorry, that permeate actually containing little, for example, like material, but actually meeting the requirement of the wastewater like recycling bag. Definitely we can use it because actually if the wastewater getting out directly from the food industry and if this water is not mixed with other like sources of water will not be contaminated. So can be reused again. Actually, I don't know the first question. Maybe I lost. Sorry. What's the first question?
It is about the safety level
The
of wastewater.
safety level, the safety of the wastewater, the water after filtered using the MBR method.
Actually, it's a good question, but this actually depends on the source. If you're talking about the food industry, I think the safety level will be high. But if you're getting from the industrial company like pulping or textile industry, I think will be a lot of the chemicals there. So we need to do like characterization for the effluent. First, we need like to get to select the membrane. Later, we'll do the characterization of the resulting effluent, and then actually we'll design because this depends on the source of the substrate of the wastewater. welcome.
So firstly we must choose our characterization the resource of the water, and then after we use MBR method we can classification what is or categorization
Yeah, exactly.
like that. Okay.
Exactly.
So
Yeah.
yeah.
You can
May
use like to do a lot of analysis for the effluent, and then you will decide, okay, this effluent is good for reuse, and or will be directed for the other applications. If not, like not used back directly in the food industry, can be actually used in other processes, which
yes.
will be also almost like clear effluent.
Okay. May I have one question again, Dr.
Yeah, for sure.
Sure. We
You
you
said
as much as you want.
you said for the next level using we must choose from the resource of the water, and in your presentation you mentioned about the classification or kind of membrane. What kind of the membrane that you recommendation to use in the to use to to filter the wastewater, and the product of the wastewater is is uh is suitable for the food processing.
Uh,
Um,
in terms actually of the direct filtration, uh, membrane already used actually in the food industry, in the beverage or the other application, already used there for the direct filtration. I'm not talking about MBR. And that mainly depend on the like call it the cut off of the membrane. First, you need to know your molecular weight of the material, and then based on that, you will select the pore size of the membrane or the cut off of the membrane for the direct filtration. And already actually for for us actually we use the ultrafiltration membrane, and we can get a lot of the rejection of the material and almost clear permeate, and use it for the lignin recovery, and I use it for the sugar recovery. But for the MBR, like usually actually we use it to degrade the material. Usually we to degrade the material, and the later we get the effluent out from the reactor. That effluent to meet the requirement, because actually each country has different requirement. For example, in Canada, say, okay, if you have effluent, for example, with the COD concentration around 3,000, for example, gram per liter, you cannot discharge it out. The water bodies or cannot be reused. For example, like that. So each requirement should be checked first, and then based on that, you need to design your MPR. See, okay, I need to use it for what, for example, in food. I need for washing. I need to use it for actually manufacturing against the food or what. So you need to check for your requirement first. Based on that, you can design the system and to select your membrane.
Yes. Thank you, Dr.
Yeah.
Bokhary.
You're welcome.
Yeah, thank you, Pak Budi.
Thank you, Bu Indira.
Yes.
Thank you for the questions. Yeah.
Yeah.
So we move on to another participants here, another questions. So there is Dr. Belladini, lovely. Is Belladini here or?
Yeah,
Oh yeah.
yeah, I'm here,
Uh,
buddy.
yeah. How are you?
I'm doing great. Hello, Dr. Bokhary.
Good. Nice to meet you, Vladimir.
Nice to meet you too. So I have two questions. So I'm such a newbie in membrane. So I was wondering, what's your thought about mixed matrix membranes or MMMs? And I just started working on using metal organic frameworks, MOFs, in MMMs. So I was just wondering, because you're an expert in this, what has been the trend on this mechanism?
Uh, Actually, it's a good question, but unfortunately, actually, I never worked with such a membrane before. Mainly, I work with the actually flat sheet membrane using polyphenylidene fluoride materials, and I work with microfiltration and ultrafiltration, and use actually millibore membrane filters. But unfortunately, actually, I never worked with that membrane before, and I don't have much experience about it. Sorry, actually, for not answering that question. Maybe Budi has some
Oh,
thought about that.
I'm not really sure. I have experience
Yeah,
to work on it too.
yeah.
So how's about
Yeah.
the anti-fouling and antimicrobial? Because you mentioned about fouling, Alnour. So is there any like solution, for example, if
Oh,
the
yeah.
also can
Actually, in
have
terms of
anti-fouling, right?
yes, actually, yeah. Actually, the guy from Ecuador, he asked her about that question, like indirectly, how we can overcome that challenge. Actually, some people working with different way to overcome the falling, so the anti-falling mechanism, and a lot of strategies there. I, I can name like many strategies used to overcome the issue of the membrane falling. Among them, like anti-falling membrane, used like to
Mhm.
reduce the falling, and mainly actually
Yeah.
modifying the main idea of modifying the membrane or manipulating the membrane somehow to
Mm.
reduce the attachment of the material of the membrane.
Yes, yes.
Yeah.
Yeah.
And I was wondering if because you mentioned about industries, right? Like
Yeah.
the member industries all across the world. Has it
Yes.
been a thing commercially to have it as a like as a metric system, or is it just like a one material based in membranes? For I'm talking about wastewater
Yeah.
technology.
Uh, actually, the second one actually already like I mean the one material based membrane already commercialized, and some companies like using membrane for commercial use and can be accessed from different companies. But the other one actually I came across like several papers in terms of the actually publication wise. They came like through several papers like fabricating membrane with different material, with different mixture. But I don't know that one reached to the commercialization or the full application. But in terms of the research wise, still like people working on that area.
Yeah, so I think it's more like a
Yeah,
research
yeah,
level still at
exactly.
this point.
Yeah, most of
Yeah.
the research, yeah, research level.
Yeah, is that okay? Like my second question is just,
Sure, sure.
um,
Sure, go
Yeah, yeah,
ahead. Go ahead. We
yeah.
still
yeah, I
have time,
wonder.
so.
Yeah, I wonder how important it is to use the plasticizing solvent when you synthesize the membranes. Because I was reading about the use of solvents like acetone, DMF, DMAC, NMP, and all that. I think some papers they kind of compare the plasticizing effects of these different solvents. So I wonder how crucial is it now? Because I'm just wondering, is it just still research based or research level, or is it already in a commercial stage? Like the use of these solvents.
Actually, that's a good question. But actually, me too. I read a lot of papers, and in full application, actually, based on my friend working on MBR, Dr. Liao, or other guys around, no one reported such application in like full scale. Most of it in the like publication level, uh, but most interesting, like more interesting results there, but so far like no full application or visualization or the stuff actually I face. Most of it like based on the just application and testing levels.
Thank you so
Good.
much.
You're
Yeah.
welcome. Yeah,
Thank you, Dr. Veladini. And by the way,
thank
Dr.
you.
Veladini is one of the postdocs in our national lab, Indonesian national lab.
Oh,
So
that's awesome.
she graduated from Virginia Tech. So she just
Oh,
graduated here.
oh, that's great. That's
Yeah.
awesome. That's great. Yeah.
So we have other questions here. Abian, so are you here? Is Abian here or I don't think he's here. So
Yes,
oh yeah, so go ahead, Abian. Oh, Isan, yes, Isan. Sorry.
yes.
Yeah, I can hear you. We can hear you. Hello, Isan?
Yes, sir. My name is Manager Varian from Agroindustrial Technology. I want to ask about how does the integration of biological treatment and membrane filtration in MBR improve water treatment efficiency compared to traditional methods? Thank you, sir.
Okay,
Oh,
yeah, actually, I got your question.
mm,
Uh, you saying the MBR, like how MBR improving the treatment efficiency compared with the conventional system.
mm,
Actually, making big shift. Definitely, membrane MBR making big contribution for the wastewater treatment. Uh, because actually, mainly right now we can handle a lot of wastewater, as then because mainly the people they have like water issues, they can recycle the water back for irrigation or agricultural application, or even back in this industry to use. For example, in the pumping industry in Canada, it was used just recycling the water back for the bulbing. And this actually depends on the application. For example, if you're using such application, you can use MPR, but in the other application, maybe your effluent can be used for other processes, but cannot be recycled back to your system. But definitely, like making contribution to the industry.
all right. So does it answer the questions, Isan?
Yes, sir, I got it. Thank you.
Okay, thank you. So we also have another questions from Abian here. So Abian is a student from Faculty of Agroindustrial Technology, and he wants to ask about what kind of wastewater is more suitable for submerged membranes or with external membranes. What's kind of the
Uh,
wastewater? I think the types of wastewater
yeah,
usually.
actually, yeah, I mentioned here for the submerged, actually for the municipal. Sorry, I don't know. I can do like this for the municipal wastewater. If you use submerged, yes, or maybe I didn't
Oh yeah,
mention.
you probably just mentioned it. Yeah.
Select. Yeah. I think I didn't mention it. Yeah, but yeah, for using submerged, actually, this is commonly used for the municipal wastewater treatment. The
Hmm.
submerged one. Yeah, commonly used. For the
Okay.
industrial wastewater, most likely applying the side stream configuration of the membrane.
Mm-hmm. Okay.
I mentioned it actually somewhere, but I don't know where. I forgot. Yeah,
Yeah.
or maybe here.
Oh,
Yeah, yeah. Sorry,
okay.
actually, yeah, I missed
Okay.
it somewhere. Somewhere.
Okay. It's okay.
Yeah, yeah.
So does it answer the questions, Abian here? I think Abian's still off of
Yes,
them.
yes, sir. Thank you, sir.
Okay, yeah. So and then we also have another one. I think this is from Bu Aisyah. Bu Aisyah, are you here?
Yes.
Okay.
Thank you,
Yes.
Mr. Budi, and thank you, Dr. Alnour. Thank you for the insightful presentation, Doctor. My name is Aisha from UNTED. I have a question regarding one aspect of your discussion on membrane bioreactor. You mentioned that the membrane material used are generally polymers and ceramic. Is there a possibility?
Actually, I
Yes,
think for me it's hard to hear you. Woody, are
Oh,
you hearing like clearly
yeah. I
to
actually can
confirm?
hear.
Yeah, that's good.
yes.
Yeah, yes, you can just translate it or convert it to me.
Oh yeah, sure. Yeah.
Yeah, yeah, go
Go,
ahead.
go ahead, Aisha.
Okay.
Probably. Hello.
Hello.
Yeah.
Yeah,
So
Okay.
are you using like the headset or something? You using headset or not? No.
Oh no.
No. Okay. Okay.
Okay.
There is a echo, so that's why it's not clear when you talk.
Yes. Sorry. The question is there are a possibility of this material becoming biopolymer or bioceramic used in MBR system, whether it will affect the treatment.
Oh, here. Her question is so you mentioned that the membrane materials used are generally polymers and ceramics. Is there a possibility of these materials becoming biopolymers, like fiber or bioceramics used in MBR system, whether it will affect the treatments? So I mean, like it's like different materials beside the ceramics and polymer. Is it possible to change it for MBR or not?
Actually, that is so interesting thought
Yeah.
to be to be converted to the biomaterial.
Yeah. That's interesting.
Actually, I believe will work differently. If you just manufactured bio-based material, I think will work
Yeah.
different. Mainly, you need to make them durable enough for the chemical cleaning and the maintenance and stuff. But definitely, I think will work. Need to be just tested and manufactured and tested. But I believe will work in the MPR.
Okay. Does it affect to the quality or the treatments or
Uh,
because
Actually,
uh-huh.
since like bio-based material can be manufactured and designed with the required specifications,
Okay.
I think that will not affect the quality of the final product. Because if
Mm,
you meet the specification for your
mm,
process, I think it will be fine. For example, if you need membrane with pore size is 1 nanometer,
mm,
ultrafiltration, for example, filter, and that material should
yeah.
be like negatively charged. If
Yeah.
you can manufacture that material with such specifications, I think you will meet the final
Okay.
requirements.
Okay. Yeah,
I think
that makes sense.
I like actually that's all.
Yeah. Probably we
Yeah,
can make another
yeah,
type of
exactly.
using
Yeah,
biopolymers or the
yeah,
other materials, right?
yeah, exactly. You can use, with
So how's
we can
Aisha?
go with the trend of the like bioeconomy and biomaterials.
Yeah. Yeah. We
With the
also need to
shift.
analyze it.
Yeah, yeah.
So how's the answer, Aisha? So you have another following up questions or
Okay, enough. Thank you, Doctor, for the answer.
okay. Thank you,
That
Aisha.
was
So
good.
Aisha is one of lecturers too in our department. So
Okay, that's good. Believe.
so we have a lot of lecturers here.
Oh
So
yeah, that's great. Yeah,
and
that's
then
good.
there is another questions here from Martin. So is Martin here?
Yes, sir.
Yeah. So go ahead. Probably can.
Yeah, okay. First of all, good morning all. Good morning, sir. I'm Martin Etans Manulang from Pajajaran University Agroindustrial Technology. I want to
Okay,
ask
that's
about the
good.
industrial sector. So I have a plan. I want to do industrial wastewater treatment between
Okay.
external membrane and submerged membrane. Which one will you choose for the application of this industrial wastewater treatment? Thank you, sir.
Okay. Thank you.
Okay. Actually, that's a good question. To select between submerge or
External.
actually, I mentioned little just brainstorming like comparison I mean differently the trade-off between. I think I put it here. Trade-off between to select either one of these configuration. Actually, you need to to consider some like point. If you were like in term of the process to be like easy to I mean to control, I think you can go for the external system because everything is outside and no need to deal with the MBR. And mainly if your system also using an anaerobic condition, I think to go for the external, I think is good option instead of from time to time opening the system and then disrupting the performance of the reactors. But if you like thinking later to be applied in full scale, you need to consider, for example, the where to be applied and the space of that area. And other like consideration, like the energy availability also there. If you like working with the submerged one, you can use less energy, and if you're working with the external one, you can use more energy. You need to like to have like some thought about that ideas, and then you will decide. But for me, if I'm operating that one, I guess I'll go for the external one, and that will make my life a little bit easier. But definitely, I have to consider the other factors such as the cost and other stuff.
So how's the answer, Martin? Does it answer your questions or not? Or you still have another one? Martin?
Yes, sir.
Yeah.
Thank you, sir.
Okay. Okay, thank you. So there is another question here. This is so interesting. It's about Internet of Things. So from Dini. Are you here, Dini? Dini Alpha. Yeah. Yeah, that's interesting questions, I think. So go ahead.
Okay.
Good morning, sir. And my name is Dini from the Pajajaran University, and I would like to ask about the implementation of automatic technology or Internet of Things or IoT in embedded system. That automatic technology this automatic technology can enhance operational efficiency and maintenance, especially in managing systems that operate continuously. Thank you, sir.
Thank you,
Yeah,
Dini.
welcome.
Okay.
Yeah, I think it's a very interesting actually question.
Yeah,
Because
IoT.
with this like increased shift with use of the artificial intelligence and this internet stuff, I think definitely in the future the people will consider like full automation of the MBR, because actually everything like repeated work, and that work can be like automated using just software, and that software can operate the system doing, for example, okay, schedule it for the cleaning, for example, like back washing after a month, automatically the back washing and stopping the system. I think with the time, that technology will in MBR, because the MBR just most of the work will be like just repeated work. So using technology will make it much easier.
Yeah, more efficient too. Yeah.
Yeah, more efficient in the future. I think so.
Yeah, I agree with you.
Yeah.
So does it answer the questions, Tini?
I think it has answered, sir.
Okay.
Thank you.
Thank you. Thank you.
Welcome.
So and then there is another questions here from Alcap. I think he's asking about the materials, the best materials for membranes here. So Alcap here.
Yes, sir.
Okay.
Okay, go ahead. Good morning, sir. Let me introduce myself. My name is Alkaf from Pajajaran University. Earlier, you already mentioned about the some materials for membrane. I would ask to you about which material is the best among the others to be used as a membrane if you consider the post-use and also the duration of the membrane sustainability.
Yeah.
Okay. Thank you for the good question. In terms actually of the sustainability and durability, I think ceramic membrane.
Okay.
Because ceramic membrane can withstand like harsh conditions, cleaning, and when like submerged or external, like will be like less damage compared with the polymeric membrane, because can be damaged easily. For me, actually, ceramic membrane is like durable material and can be like used for long term. So it's good of the sustainability and other perspective. But in terms of the like flexibility, I think polymeric membrane is good also in terms of the other ways. But in terms of the sustainability and long term operation, I think ceramic membrane.
Yeah, that makes sense.
Yeah.
Is it good? Alcap?
Yes, it's very clear. Thank you, sir.
Yeah, thank you. So we actually still have 4 more minutes, and now we have 2 more questions here. I think one question, 1 minute. So the first one is from Widyarti Putri. So Widyarti Putri here, or is Widyarti, are you here?
Yes, sir.
Okay, yeah, go ahead.
So let me introduce myself. My name is Widyarti Putri, and I'm from Pajajaran University. So we all know that there are two types of membrane bioreactors, the submerged and the external. The external membrane bioreactor offer more features compared to submerged system, but using a higher energy consumption. So the question is, how can external membrane bioreactor be optimized to reduce their energy consumption, and how would this optimization affect the life cycle of environmental impact of external membrane bioreactor? Thank you, sir.
You're welcome.
Yeah.
Actually can be optimized. I mean, in terms of the energy consumption. For the external, actually, this issue mainly, let me say it in other ways. These issues can be solved. For example, if we working with the high strength wastewater, that means we can generate a lot of energy actually using anaerobic MBR. So mainly the issue with the external one because the cost of the energy and other stuff. So if we can handling high strength wastewater, we can generate enough energy. That energy can be used for the system. Most likely will be like sufficient enough to operate the system.
Mm.
In terms of other like development in the like external MBR, I think as mentioned before about the development of the like artificial intelligence stuff and operation, guess would be like a automated system and then reducing the interval of the cleaning and interval of the operation. Everything can be optimized for the best for the optimal condition. I think so.
Yeah. So is it clear, or you have other questions, Widyarti?
I get it, sir. Thank you, sir.
Okay,
You're
thank
welcome.
you, Widyarti. So the last one, we have George here. So George has to do.
Yes, okay. Thank you for
Oh,
the
yeah,
thank you for the opportunity, Mr. Budi.
yeah.
And for the last question, I think I want to ask Dr. Bukhari a simple questions. I'm just wondering, well, you said in the membrane folding, the material is cause a blockage in the membrane, right? But
Yes.
I'm just wondering, is there any materials or any particular materials that can be dangerous to the membranes, or you can affect or you can damage the membranes? That's all my questions. Thank you.
Thank you, George.
Okay, thank you. That's a good question. Actually, in terms of the damage, so far like the material in general, like when getting inside the membrane pores, mainly clogging that pores. Clogging the pores, when getting inside, the main damage will be like no flux, reducing the flux. But in terms of affecting the membrane material, actually, I think the membrane material is like good enough to withstand, even because we are applying chemical cleaning. If the membrane can not be affected with the chemical cleaning, I think any other material clogged inside the bore will not make any like obvious damage on it. Sometimes actually when operating under I mean high temperature, the temperature can expand the membrane and changing some structure of the membrane. But the material itself, I think, will not causing any issue with the membrane because the membrane is designed for the tougher conditions, for chemical cleaning and others.
Okay.
Yeah.
Okay. So how's the answer, George?
I think that's enough. And thank you, Dr. Bukan and Mr. Budi.
You're welcome.
Thank you, George. Thank you so much. So wow, it's already 7 here, and it's already I think 10 a.m. in Indonesia. Wow. So we
Okay,
actually have
we
a
use
great talk today. Yeah.
we
We have
used all the time. That's
all the
great.
times and a lot of questions too today. Wow,
We use
so
all the time.
tiring, but it's so excited, so interesting. I know like
So
membrane technology is something that I really wanna work on it. So when I was in master degree, and I actually took one of the courses. It's about membrane technology, and then I used to teach membrane technology as well in our department. But honestly, actually, I haven't had an experience to do the experiments in the lab. But Dr. Alnour here, he's an expert at the membrane technology since he was in master degree, right? So you already
yeah, I
started
work with
your
membrane.
yeah, you work on membrane technology since you were in master. So we
Yeah, work with
actually here we'll learn a lot of things about membrane MBR, and we call it like that one is the hybrid process because they are two technology, membrane and bioreactor. So it combined
yeah.
together. So that we call it MBR. So, and thank you so much, Dr. Alnor. And so,
You're welcome.
your
Welcome.
talk is so insightful, and we'll learn a lot of things from you. And then, so,
You're welcome, guys. Yeah.
yeah, and then for the next meeting, we will have another a great speaker as well. He's our friend, Dr. Arnold's friend, and my friends too. So he's Dr. Fuad, and he's a postdoc in Pennsylvania State University, and then he will talk about gas fermentation bioreactor. So we already learned like anaerobic digester, and then today, MBR, membrane bioreactor. And then for the next meeting, we will have another types of the bioreactor, which is for gas fermentation. So that's so interesting. And today is so interesting. And then for the next meeting, it will be interesting too. I really hope that you still attend our meeting. Sorry, our lecture.
I
Yeah.
think we talk actually I recommend
Uh,
all of you for our presentation because he's a great speaker and he will deliver definitely good
yeah.
presentation
Sure.
for you guys.
Yeah. Sure.
Yeah.
And then probably some of you still want to have some questions. You also can share your email address probably to them, right? To the audience here.
Yeah.
Okay.
You can share.
Yeah, yeah. Probably you can write it down, or probably I also can share with them. And then I shall
Yeah.
also share your email to them. So that's
Sure.
gonna be good. I mean, if you still have more questions and whatever, just ask Dr. Alnour. He is expert at membrane bioreactors, and then he's also work on pre-treatment biogas for the biogas production. So his project is about the pre-treatment. It's same as Dr. Usman,
Usman,
our last speaker. Okay, thank you so much, Dr. Alnur, and thank you for
You're
coming
welcome. Okay.
here today for the audience, and we can continue our lecture. We still have two more lecture. Thank you so much. Thank you for today.
Yeah, my pleasure. Thank you
Yeah.
guys and
Okay.
have a nice rest of the day.
Yeah. Have a nice day too, Dr. Alnur. Thank you so much. Bye bye. Bye bye.